Okay.
In 10 minutes or...
No, let's start.
Let's start. In this class, we will talk about 4 aspects. One is corridor selection. 2 is site distance. 3, highway alignment and practice problem. We know that highway alignment involves the decisions related to choosing an optimal position, given substantial environmental and design considerations. Corridor selection is comprised of the broad task of choosing a highway location through decisions relating to minimizing cost and impact to the human and natural environment. The engineering computations of such corridors are derived from consideration of highway consideration, segments as channels. So, channels calculations are based on geometric and trigonometric principles. This we should know. Geometric and trigonometric. Horizontal alignment elements in the plan view and profile view. This is horizontal and vertical. Components, each if the affect the highway location and require an iterative process to balance the various quantitative measures and trade-offs of particular alternatives, as well as include feedback generated from stakeholders in the public involvement process. So, at any point along the highway, the driver X distance from the beginning of the vertical installations or feet AB is coefficient defined below. Just the parameters we should determine according actual considerations. C. Elevation of the PVC. C is the PVC elevation, because X is equal to 0 correspond to the PVC. When we set X is equal to 0, we can get Y is equal to C. Yes or no?
Yes.
Okay. We can use these formulas, function, parabolic function. We can got and the PVC X is equal to 0 and Y is equal to C. So first derivative, the slope.
That is the slope.
We can got and the PVC X is equal to 0 and
dy
is to
dx is equals to b is equals to g minus 1.
is to G1. Yes or no?
Yes.
Okay. And this is the first. And the second derivative, the rate of the change of slope. We can got it everywhere. The second
this
derivative
d2
is equal
y
to
over dx squared.
2 times a. We can use this relationship g2 minus g1 divided by L, and a is equal to this.
Mm-hmm.
Yes or no?
Yeah.
Okay. So we use this function, the parabolic function. We can, according to these conditions, to determine C, B, and A. And when we know the C, G1, G2, G1, and L, we can got A, B, C. We can get. So, we know that this general equation can be modified for each individual curve to describe the relationship between the distance x and the elevation y at any point along the vertical curve. The term x is used to denote any horizontal distance along the curve and is bounded by 0, which would
Designate.
by PVC point, and the length of the curve, which would designate the PVT point. The term A becomes the tangent offset, the change in elevation from the tangent to the curve, and the rate of G1 replaces the term B, and C becomes the elevation of the PVC. So the parabolic equation will enact specifically in terms of vertical curves takes the following form. Is right?
We don't know. Yes.
We can know that C, G,
2. Okay.
A, B, C.
Mm.
We can got this in another form.
Mm-hmm. This is A. This is B. Then
This
that's
is
C.
A, B, C.
Oh.
So we can know from these formula or equations easily. Okay. Some additional properties of vertical curves can now be formalized. For example, offset, which are vertical distance from the initial tangent to the curve, are extremely important in vertical curve design and construction. But from this, we can know how far this offset we can get. Question why? Which is also important. Offsets for equal tangent vertical curves. How to calculate or compute?
I should say that again.
How to calculate y or ym?
Okay.
Or compute?
Y. We have L2 and we have a bigger L. And we have X. It's what? Opposite.
But we should know what does this mean.
First. X equals
G1, G2 is like before. Y is offset at any distance x from the PVC in feet. Ym, middle curve offset in feet. And like this from PBI to the curve. X is distance from the PVC. L is the length of the curve in stations. PVC, PBI, PVT is like before. So we should know how to calculate or compute Y or Ym. From this, we can use this formula to calculate Y, Ym, and Yf. But we should know that G1, G2 in percent, L in feet. A is absolute value of the difference in grade expressed in percent.
Percentage.
Like this. But this absolute value, it is when we calculate Y and Ym, we should first to calculate or get A. We should know G1 and G2. Yes or no? Yeah. Yes. When we get A, when we should use this formula to calculate Y. So X and L is we know, and Ym is
L.
8 multiplied by L and divided by 800. This is we let X is equal to
Sorry.
L divided by 2. Just like this, we can got Ym. We let X is equal to this. Divided by 2.
L is X.
Let X is equal to
L divided by 2. But there's a difference.
divided by 2, we can get Ym.
Huh.
Yes?
Okay, I don't get it.
Ym is
L.
when X is equal to L divided by 2 is the mid of the
Okay. But right now X is not equal to L divided by 2. Alright. When? Okay. So, Laushi, question. So, these figures 200, 800, and 200, are they fixed figures?
200.
Yes. 800, 200. Are they fixed figures?
Yes.
Or they are fixed?
Fixed.
Okay. Well,
They are fixed, so we should
know them.
change it.
Okay.
It's 200, 800, and 200. So when we know L and then G1 and G2, we can get Y, Ym, and
YF.
YF. So by setting this equation equal to 0 and executing the vertical curve specified components for A and B. The equation for the location of the high or low point can be determined when we use the first derivative is equal to 0. We can know the low or high point of the curve. The parabolic equation can be used to determine the elevation at this point. The high point can be identified for crest curve.
Crest curve.
Crest. And the low point can be found for sine curve. These points are never above for crest curve, one below for sine curve, the PVI. Identifying and locating the high or low point of a vertical curve is important for drainage considerations. This is for drainage considerations and for determining where the appropriate clearance is provided. Appropriate clearance is provided underneath an overhead structure or on top of underground utilities. So, we should identify and locating the high or low point of a vertical curve. It's important. One reason is drainage consideration, and another is the appropriate clearance. So we should consider these two aspects.
Record. 5, 4, 3,
The following
1.
process
Yeah, this is E max. Is E max. Yeah. This when we have the if the rows have the not in the center, if the rows is not in the center. The nose is at this place. This the Q. This is the E. It's not in the inclination. Inclination E. So the pressure. That's this one. Okay. So in this case, we just the first step we want to study this shaper, this examiner. The nose is at the center of the foundation. The nose is at the center of the foundation. So the pressure is in the line. The temperature of the foundation is the line. The line. Lining. When you add the Q, increase. When you increase the Q, then with the foundation we are done. The segments, the gradient we are yeah. The foundation we are down. We are down. Okay. So this wow. This is the segment. Segment. So You can say one, yeah, give them a load on the foundation, so we are down. Okay, if they we will add the loads, so the grade, the sediments will increase. So then we can call this line. This is 0. This is sediment. This is the Q unit. This is node. So in the first step, we add a small node, so small node, Q1, Q2, Q3, Q4, Q5. Yeah. So we can all the segment, set 1, set 2, set 3, set 4, set 5. Okay? Yeah, this is 1, this is 1. So then we got out the cover, So this is the QS. This is the QS tower. This is the sediment of the foundation. When you add the curve loads, maybe with the 9, with this one, with this one. Obtain the foundation is foliar. Obtain the foliar is foliar. So, when you design the foundation, when you below the Q, maybe you can calculate the segment of the foundation. Okay? And first step, you will know this QS9, QS cover. When you design the foundation, you don't know this cover. So you can't calculate the segment of the foundation. Maybe you just know the load, but you have no cover. Maybe you can't calculate the base. So this cover, where does it come from? Just for the in-shoot test. This is our direct method to determine the sediment, or determine the bearing capacity of the foundation. This is a direct method. Okay. And when you have no foundation, you have to design. So then you only show the shallow method to calculate it. Yeah. Okay. So in this process, we just have to introduce of the shallow foundation. Sediment of a shallow foundation divides into two large categories. You can say elastic or immediate sediment. Elastic or immediate. Second is the consolidation sediment. Yes, occurs over time. This elastic or immediate sediment takes place during or immediately after the construction of the structure. Construction or the structure. Yeah, for nitrogen. This is the foundation. Yeah. We add the node just the moment. This foundation will have of elastic or emitted sediment. But we keep the nose. The foundation will have the sediment during the time. When the 1 year, 2 years, 3 years, the sediment will down with the time. We're down with the time. This is the consolidation sediment. Okay? Yeah. So the total sediment of the foundation is the sum of the elastic and the consolidation. Yeah.
Can you have this kind of displacement, like lateral one, horizontal one, like the foundation?
That's the foundation.
Yeah. Right now it's down, right?
Yes, it's down.
Vertical one.
Yeah.
So is it possible to have
Or lateral force.
Yeah.
Yes, it's another question. Yes, it's another question. Okay, because usually in the channel foundation can support. Usually use the kind of channel foundation to support the lateral force or horizontal load. Yeah. When the foundation was building, how much lateral forces or lateral load, then we use another types of the foundation, like the depth foundation, pile foundation, or the castle, and so on. Because the shallow foundation usually supports much lateral loads, lateral loads. Okay, yeah. So in the shallow foundation, just focus on the sediment and the bearing capacity of the foundation. Okay. This is 2 questions. This is you say the lateral displacement of the foundation is under the lateral horizontal loads. This is another question. Okay. Yeah. So in this one, so the sediment have the two major categories. Elastic or the medial sediment consolidation. So really the condensation sediment is the have more 主要的 and major the sediment is the major sediment is the consolidation. Yeah. 主要的，它是占了主要的，它占了主要部分。
The maximum.
Yes, maximum. Yeah, and maximum. Okay. For the consolidation sediment, I will class it into two fractions. Is the primary. The first one is the primary. Second, first segment is more significant, and then second segment in organic clays or sealed solidus. Yeah. Secondary occurred after the primary sublimation caused by slippage, and reformation of soil particles and such containers. So second consideration is more significant in organic soils. Yeah, significant. Okay. First one, we will to calculate the elastic sediment of the function on saturated clays. Such case we are using Poisson ratio. Poisson ratio is US is 0.5. So this was the average sediment. We just use the average sediment of flexible foundation on saturated clay soil is given by the equation. This is one. This is the elastic sediment A1, A2. A1 and 2 is this equation, and the L, and this L is the length of the foundation, B is the width of the, DF is the depth of the foundation, and H is the depth of the bottom of the foundation of rigid clay. Q0 is the net load per unit area of the foundation. That's Q0. So US is the pressure mass, of the soil, base mass. We can kind of test it, the ES from the indoor test. In the label, we can test it how the consolidation test during the experiment in soil mechanicals. We can test this one, this one. Okay. So values for the parameter equations provided to be highlighted on this line. We count A1 use this cover. Yeah, A1 is have the relationship to the H by B. Yeah, for the foundation, H and load. This is the H. B is the width of the foundation. So we know the foundation, the width and the depth of the foundation. So we can count the A1. Same to the A2. A2 is the DF and the B. DF of the B. DF of the B. DF by B. Oh, sorry. And this H is not. This is DF. Okay. Sorry. DF. And this is right. Maybe this variation is like this one. The foundation in play. The foundation in play is like this one. Yeah, this is B, and this is, yeah. This is the cover. This is the cover. Okay. This is foundation in place. Okay. In place. Rest of the foundation like this one. Yeah. And H is depth of the boat of the foundation to origin to clay. Boat of the foundation to origin to clay. Maybe it's yes, it's like this one. This one. Clay. So this is the. So for like this is rocket. What had the gravel and so on. And so on. Okay. And so use this cover. For this is for the circle. The foundation shape of the circle. This is for the square and for square and so on. This is A1. A2 is use this man. Cover. This is the depth. And the by B is the width. So from the cover we can see when the DF by B when we reach it to K, we can see the A1 maybe keep the same. Yeah, keep the same. It's the same. So when you can see maybe reach it to BF by B is like K. So we can see. So this is the values for the A and the B. So in this version A and B we can know. So Q0 Do you know how to calculate Q0? Do you know? Q0, we will, no, have no table. Q0 have no table. We let's say the Q net is the, this is Q net is the Q. Do you know the Q is gamma, the DF? Uh-huh.
Gamma GF, yes.
Yes, this is gamma DF. Q net, which is the Q net?
It's Q alpha minus Q.
Minus
the
one.
net load, right?
Minus one.
Net load.
Minus which one? Minus which one? Yeah, the same chapter 2. Chapter 2. Okay, you can see.
Q minus Q, whatever is Q net. QR is supposed to Q over QS. Net increase, net stress. Not really. This one. Q minus Q.
Yeah. Q net is this one.
Q minus Q. Vector safety.
Q net is QU minus Q. Yeah, minus Q. Okay.
And
The market, you can market, you can see this is right. You can right. You can go out to the 环宇城，环宇城。You go to there, the best. Yeah, but at the restaurant door of the square, nearby the station of the Shanghai station, metro station, nearby the metro station. And the ordinance, yes, on the other side of the ordinance, yeah, you can see this is right, this is right. This is this one with a sniper, with a base point, okay. In Chinese, it uses the 箱型技术，箱型 like a box, okay. Numbers of the matters may be supported by PAS, which help reduce the settlement of structural building of highly compressible soil. If the soil has a consolidation, we have the sediments or big sediments. Then the mat foundation cannot reduce this sediment because the soil is so thin, so soft. It's so soft. So then we can use the pipe only at the bottom. Then we can transfer the nose to the depth on the ground. Use the pipe. And then at the top of the pipe, then we can construct the mats. So this is another consistent foundation. Consistent 组合型基础 consistent 组合基础 combined foundation. It's not the combined footing. Not just this combined foundation. Yeah, use either the pie foundation and the mat foundation. Okay. Yeah. This one. Another is where the water table is high. Now matches are often placed over pies to control bias. Yeah. If with the bias, But is the part, the foundation we are go up, it's not sediment. It's not with the water table, when the water table is increases, it increases. So the foundation is like the box. Yeah. Yeah, like this, that's the foundation. Yeah, because the box, the end of the foundation is empty. Is empty. So when the one table is at this place, at this now, so how with the bias is the one of all. Yeah, but well, the foundation we have go up, we have go up. So then we can use it, use our foundation, use subtract, then we can have the pi, and then, so the pi, we are supposed the, propose the tension of the biasing, branch. Okay. As I could this figure, this figure shows the difference between the depth df and the rise p of the azimuth foundation and the web foundation. So yeah, this is the b. B is the rise of the footing. Rise of the footing. This is for the footing or azimuth footing. So the depth is the footing depth is and this depth. That's this part. But for the mat foundation, well, this is the line of the ground line. Yeah. So the depth of the foundation is from the surface to the bottom of the mat foundation. And the mat foundation, the rise of the mat foundation is from this side to this side. This is the rise. So the rise is bigger than the footing. The depth is bigger than this one. Okay. So when you design the channel foundation, maybe you first step you determine the steps of the foundation. Maybe it's footing, azimuth footing, combat footing, and with the mat footing from the mat foundation, or with the snapper or basement snapper or the box footing from mat foundation. Yeah. Okay. So this is the difference between the footing and the mat foundation. Okay. Yeah, this is our flat mat foundation and this construction. Yeah, this is so this is the board snapper. Then we are doing our wall. With this direction and with this direction. This is the column. This is the column. And the top of the foundation, we are having our top snap. Then then we start to up with the strut as a section. Yeah. Okay. When you design the foundations, first step you have to determine the bearing capacity of the foundation. Yeah. For the mat foundation, the gross ultimate bearing capacity of mat foundation can be determined by the same equation used for shallow foundations, like the Tasaki equals or the May-Hofreis equals. So you can see this equation is whose equation? Whose equation? This equation.
May-Hof.
Yes, this is May-Hofreis equation. Yeah. So in this equation, you have the factors NC, Q, N gamma is the bearing capacity factor. Yeah. So this is shape factor. This is depth factor. This is inclination factor. Yeah, this is inclination factor. And so on. Yeah, correct? Yeah. So using this equation, we can calculate the Q bearing capacity, Q ultimate bearing capacity. Then by use the net ultimate capacity of the mat function, use this one. Use QU minus Q. How to calculate the Q? Q is the gamma
Gamma minus
multiplied the depth df. Yes.
Df.
Yes, it is equal to df. For example, when the soil of the ground is saturated, is saturated place, then we can know the friction angle is 0, and a vertical load condition using the equation we see the determine to determine the gross automatic capacity we find the Q equal just this term because the from 0 braking angle is 0 and have no inclination loss, so this one is 0, so this one is 0, so this one just 1, so only have this part C prime times NC, FCA, FCS, FCD, FCI, and Q. For saturated with azure, so to calculate the QU. So the CU is undrained cohesion, Then we can find the undrained cohesion in C is 5.4, 5.4, MQ is 1, and gamma is 0, So, and the FCS, FCD, FQ. Then we can got the Q. Take this 5 minutes to do this equation. We can got this one. Okay.
Sorry, can we go back? I want to ask about
This one.
no.
Next one.
Yes.
Yes.
CU and drain
Undrained cohesion. Undrained cohesion is about the test method of the sharing test. To test the shear strength of the soil. Use the tracing or direction shear strength test.
Okay, so right here, right? It's CU. Which one is the answer now? Because we have NC and NK and NY.
NC, we can find this back from the table.
Yes.
The whole is table.
Yes. So,
Yes.
so which one is the answer for CU?
And for CO, as CU will tell you, you must to test. You can take the sample to the label, then we can test the strength of the soil.
Yes, the C.
CU is the index of the soil strength.
But yes, this which is okay. What I'm asking is, since look at the equations, right? QU we have the formula, so CU we don't have the formula. Just in simple terms. CU, do we have a formula or not? Like, or it doesn't need a formula?
QU.
Yeah.
QU this is
It's already given in okay. Thank you, like.
QU is this one.
Yes.
Just this C prime. Then we use the CU to replace the C prime. Okay. Because the C prime is based on the condition of the foundation. If the condition is under the ground, under one table, so the soil is saturated. When you add the loss at the moment, so the water the water in the soil cannot draw out. So then we to what is the condition of the ground. So have the test of the CU test. So this test method just reward the condition of the foundation condition. Okay.
Yeah.
Okay.
Yes.
So then we can use the CO, ungenerated cohesion. Maybe if the node add the node have a non time, so they go out, the water is go out. So the water go out. So we use the CD. So this parameter use the CD. This is CD. CD cohesion. CD cohesion.
Sure.
Yes.
Okay.
Okay. I'm trying in this formula, on this equation, and this equation, the factor of the safety, so we use it to calculate the net available bearing capacity. For max as on claim, the factor of safety should not be less than 3. Under the dead loads or maximum level loads, so under the most extreme conditions, the factor of safety should be at least 1.75 2. Yeah. So usually we use it for FS is 3. Yeah. For matters constructed over sand, our factor of safety of 3 should moderate use it. And most working conditions, the factor of safety of the bear capacity on sand is very large. Yeah. Okay. So this is for just for this condition. We should use it with the saturated glaze.
Yeah.
If the soil is not saturated glaze, so the African angle is not 0.
Yes.
So then we can go back to use the Morpheus equation to cut it. So NC, AQ, A gamma is not 0. AQ is not 1. So using the Parabol equation, we can get the ultimate bearing capacity as Q net is QU minus Q. So then we can get this formula. Okay? So if Fs is 3, the order soil bearing capacity is Q net, use the QU net minus by Fs. Then we can get the Q net net ultimate capacity. Okay. So the net oil bearing capacity for to construct over granular soil depends. It can be determined from the standard persistent resistance. Use SPT resistance numbers in 60. Yeah. This N6 is standard penetration resistance. This is an inside test. Inside system. Inside system. Yeah. To take this, so then we can use this formula to calculate the Q net directly. Okay. So this is the vice of the foundation. FD is this one. FD is the statement. Yeah. So let's use this formula to calculate for the granular soil deposit soil. Okay. Okay? Yes.
And infiltrate into the soil. And we can see this suspended water in this area. And this is phreatic surface. And this huge. And there are others. It's free flow well and river. So from this figure we can know that the water is distribution in the different parts of the foundation. Source of subgrade water. Natural water contains of natural soil.
Atmospheric.
Atmospheric precipitation, surface water, groundwater, capillary basin water, steam condensate, film moving water. This is the water. The source of submarine water and conditions of submarine water temperature and exchange. To combine the actions of groundwater and the temperature on the change of submarine humidity. The most typical phenomenon is frost heaving and frost burning of submarine. We can make is frost amount and the slope. So the water temperature are very important. When we perform the design of submarine, we should consider the highway in the area which is the water and the temperature. In the north, we should consider the frozen damage. But in south of China, maybe we should consider the water. But the frozen we can not conceive. Temperature, cost is the temperature stress and the deep segmentation of cement and pre-pavement. When the temperature is the temperature increases, the cement concrete will incapacit. So when it is confined, the stress will increase. Temperature causes accumulated plastic deformation and low temperature cracking of asphalt concrete pavement. So the temperature, this is the expansion damage of cement concrete pavement. And this is the low temperature cause the cracking of asphalt concrete pavement. Influence of humidity or stability of subgrade and the pavement. The influence of humidity on subgrade, softening, frozen, and unstable. It is necessary to set up good drainage facility and control the dry, wet types of subgrade. When the subgrade, just like is in dry conditions, the strength of the soil is large. So it can occur this damage. The influence of humidity on pavement, moisture is accumulated in the subgrade and pavement, which reduces the strength and stiffness of subgrade and pavement, and cause pavement damage and further increase the permeability of pavement. Dry or humid type of subgrade. This is the properties of soil. we should know how to calculate the natural density, liquidity index, plastic limit. We should know how to use this formula to calculate. We can know that this L is liquid limit,
Yes, I'm
P
taking a picture.
is plastic limit. Plastic limit is in Chinese is 缩线，
Sure, shit.
对，竖线。然后呢，this is liquid limit 就是液线，
Yes, yes.
对，液线、缩线。
Sure, shit. Yes, shit. Plastic, liquid.
And we can
Plastic.
use
Yes,
this
sure.
when we know ohm L and ohm P and the natural water content. This is natural water content or moisture content of soil. We can use this to calculate liquidity index. And when we calculate liquidity index, when it's less than 0, it's semi-solid state. It means that the soil is in semi-solid state. When it's between 0 to 1, it means that the soil is in plastic state. But when it's larger than 1, the soil is in liquid state. And we can divide the plastics in 3 different grades. One is hard plastic, and soft plastic. Just like this. When we know that, from this picture, when the soil, the water content of soil is the shrinkage limit, is in solid state. With the water content increasing, it's between the shrinkage limit to plastic limit, it is in the semi-solid. With the water content increasing from plastic limit to liquid limit, it is in plastic state. But when the water content of soil is larger than the liquid limit, it is in liquid state. So, another index is plastic stick, is the liquid limit minus plastic limit. We can got plastic limit. So, from this index, we can know that absorption capacity of bound water, viscosity, roughly reflect the content of clay particles. From this parameter, we can know absorption capacity of bound water, viscosity, and roughly reflect the content of clay particles. Now, from this picture, we can know that then In Chinese, can we know? 详结河水。
会水像
Strongly bound water.
会水
And the soil particle, when the soil is in solid or semi-solid state, the water in the soil is in joining bound water. And with the water increasing, it can be in plastic state. Expect the soil particle and strongly bound water, there were loosely bound water. 弱结的水。So from this picture we can know that the water film on the soil particle is increasing. And with the water increasing, there were free water. Just like this. So we can use this consistency stage and a form of water in soil, just like strongly bound water, loosely bound water, free water. And with the water content increasing, the state is changed. And the consistent limit is this straightedge limit, and omega p is plastic limit with a maximum strong bound water film. It means that the strongly bound water, the film is maximum, and with the water increasing, the more loosely bound water.
free water appearance.
So the consistency of cohesive soil reflects the form of water in soil. So this is the fine soil. But for coarse soil, we can not use this index to describe. We just for clay. Okay. That's over. We'll continue in the next class.
So in this one, this is a node Q0 is use the Q0 EQ the Q, this road by arrow and gamma E F. Yeah. This is the Q. This is the Q. So this is the Q load. So from the ZQ is the load, vertical load, divide the arrow. Here's the arrow. Okay. This is the Q0. Oh. This is the Q0. So B, ES is a model. Yes, yeah. Not Young's model. Yes, it's a consolidation mode. No, model, consolidation law.
Consolidation law.
Yasu model. Okay? Consolidation road is so your mechanicals. I don't know this one. Yeah, the next system. So we just know the ES. ES, the most of the elasticity of the loss. Yeah. And because it's the elastic segment, not the consolidated loss. Okay, sorry. Yeah. So it's just to calculate the elastic segment on the cell. So the most of ES of the elastic for the for such a place is given by the equation. So this equation, yes, Cu is an undrained shell stress, undrained shell stress. Undrained shell stress in the erect shell stress and the texture test. Texture test. How the undrained undrained 不排水 undrained when you test them undrained you test and beta the value of beta is our function of the plasticity index and the overall concentration was the R and our consolidation ratio. And its general region is given in the table on the following slide. Yeah. So this is the value of the beta OCR. OCR, in the soil mechanics, you can review it. How to calculate the OCR? Okay? Yeah, OCR. Yes, it's about the frictions, consolidation pressure, or pre-consolidation pressure. To divide the self stress. Okay. So we can find it from the table. From the table comes the value beta. Yeah, so ES and ES no. Q0 we can use this one. B is the value A. So then we can use this equation to calculate the segment. Okay? Okay. Have a rest, okay? Yeah.